In example 4, we were looking at how all of these are equal amounts, but so they're equivalent in quantity or length, but they're all cut into different amount of pieces, and so they're represented differently, or they look different, even though they all represent the same amount. In example 5, let's take a peek at that too. Let's keep doing that. Give 2 different representations for the value indicated. Okay, when I take a first glance, they both look like a half. So my first representation is going to be a half. And then in this situation, I mean, I might as well, I could cut it, as long as I'm cutting into equal pieces, I can cut it however many times I want. But let's just suppose I do what all of my students usually do, and I just cut each of those into half again. Then I have quarters, and now the shaded region of this whole rectangle is 2 of the 4 quarters. And then over here, I have 24 stars again, just pictured differently. And this is 12 of them, 2, 4, 6, 8, 10, 12. 12 out of 24 stars. 12 stars out of 24 stars is half of the stars. So 2 different representations, still indicating a half. We could have probably even rewritten these stars as 6/12. That makes, and I want you to know that, you know, these stars, I use stars and I use random rectangles, but in the reality of the situation, when we're using these in real life, these have very, I mean, usually they're, instead of stars, they're humans. And instead of, I mean, who even knows? Like, area is so applicable, like farmland. And I mean, there's just so many applications to area that I can't even, I mean, painting, whatever. So even though these are vague and may not seem relatable, these are actually just representations of what we would really use them for and apply them to any situation. Write a value representing a birthday candle's burn rate of 2 inches in 12 minutes. Okay, now this is where things get a little bit interesting, because all of a sudden we have 2 inches in 12 minutes. And if we are being asked to write a value representing this, we could write it as a fraction, where if I include my labels, 2 inches in 12 minutes. Now, there is something very peculiar about this, and that is if I left off my labels and wrote 2/12, 2/12 of what? 2/12 of an inch, 2/12 of a minute. These 2 labels or units are not matching. They are not coming from the same hole. Up here, it was half of an inch, and they were the same hole every time. 1 out of 2 pieces of an inch. 1 piece of an inch out of 2 pieces of an inch. 3 pieces of an inch out of 6 pieces of the inch. But here, not so much. And when we see this, and it doesn't really make perfect sense as 2/12, then really what we're doing is we embark on ratios, okay? So even though these ratios, people write them in fraction form, we really do need their labels in order for it to make sense. This really doesn't make sense in the context of the situation. Saying 2/12 doesn't really convey the idea of 2 inches in 12 minutes. Now, this will work as an equivalence. If it's 2 inches in 12 minutes, then it's probably 1 inch for every 6 minutes, if it's a consistent rate. So it does work like equivalent fractions, where I scaled this down. I glued every 2 pieces into 1 by scaling down like this. Yeah. And another interesting thing about these ratios and how they differ from fractions is that if you wrote the reciprocal, so maybe you wrote 12 minutes in 2 or for 2 inches, 12 minutes for every 2 inches, better said, then this has the same meaning as this. So 2 inches in 12 minutes has the same meaning as it takes 12 minutes for each 2 inches. These represent the same growth rate, even though as fractions, 2/12 is very different than 12 halves. So again, I wanted you to see the difference between what a ratio, so a ratio where there are different units and different labels and different wholes, versus a fraction where we know what the whole is and we should label the whole every time. So even up here, our whole was an inch. This would be a ½ inch, 3/6 of an inch. Okay, so labeling these wholes, that's a good idea in general. Write a value representing the pay rate. Now, again, I see this word rate and I see dollars and minutes. So I know immediately when I have 2 different units, I have another ratio. And I'm going to need to label them. So label, label, label. This class is all about labeling because everything is in a situation. So let's see. $10 in 60 minutes, or equivalently, a lot of people prefer to rewrite 60 minutes as 1 hour, or equivalently, a lot of people, like to write $10 per hour. Okay, all of those are equivalent. You could have written you could have written $1 for every 6 minutes. You know, like if you're a lawyer, you charge by, or if you're a professional athlete, you charge by the minute. Nonetheless, all of these are okay at representing this, and the reciprocals of these would have the same meaning. So there you have it. The difference between ratios and regular fractions, these require one label because the numerator and the denominator are out of the same whole. Ratios require 2 labels because they really have different units at play. Okay, I have several remarks. So let's jot them down and talk them out. First, to compare fractions, they have to come from the same whole. It doesn't make sense to compare inches to feet, ½ an inch to ½ a foot, unless you actually say it like that. But if you're going to compare a half to 3/4, they need to be from the same whole. To compare fractions, they must be from the same whole. Okay, and along with this, I'm going to say it again. Label everything. Know what your whole is. Know what your units are. Next thing that I feel like is remarkable about fractions, portions or measurements must be in equal amounts. A lot of people screw that up. Portions or measurements must be in equal amounts. Okay, this is like the idea of giving an unfair advantage, and then it kind of takes away the meaning of the fraction altogether. Equivalent fractions without the whole. So let's remark on that quick. Okay. At some point, you have to get to the level where you are going to be quick about the fact that you're just going to write equivalent fractions and not have to draw an image and actually measure it out. For instance, suppose for fun, we have 3/7. Then if I take every single piece and I cut it into 2 pieces, that means these 7 pieces will become 14 pieces because I split each one of those into 2. And these 3 pieces will become 6 because I split each one of those into 2. And now it's this equal amount. It's just that these are more of the smaller pieces to make fewer of the bigger pieces. Nonetheless, if we scale them up by the same amount, this multiplication or scale up by 2 really represents the fact that I took every piece and cut it into 2 pieces. So preserving the actual equal amount, just more cuts. And then let's suppose for fun we have something such as 22/44. So pretty refined pieces. And I can actually simplify it. So here's what I mean. If I take every 2 pieces and glue them into 1, that means 44. For every 2, I'm gluing them together to make 1. So 44 will become half as many, which is 22. And if there were originally 22 pieces, and from every 2 pieces I make 1, then I will have 11. And now I can actually do this again. If I take every 11 pieces and glue them into 1, this will become 2, and this will become 1. And so this got, by gluing pieces together, even though they're still the same quantity, all of these 3 fractions are the same amount, or equal quantities of whatever we have, I went ahead and scaled down, making it less refined pieces, or bigger pieces actually. I scaled down by 2, gluing every 2 into 1, and then I scaled down by 11, taking every set of 11 pieces and making 1 out of them. And that would be just simplifying it. A lot of people have an easier time relating to a half rather than 22/44. Okay, another remark. Let's go, how do we change mixed fractions into improper ones? How do we change mixed fractions into improper ones? Okay, I'm going to show you how I would do this. A mixed fraction has wholes and portions. So let's suppose I have 1 and 5/6. Well, if this is cut into 6 equal pieces, and we only have 5 of them, I'm going to cut this into 6 equal pieces, but we have a whole, so that's 6 out of 6 pieces. So really we have 6/6 and 5/6, and that makes 11/6. Now, I want you to know that a lot of teachers teach this shortcut where they say 6 times 1 makes 6, and then 6 plus 5 makes 11, and now you have 11/6. But really what that's doing is this. When you multiply 6 by 1, you are saying that there are 6 pieces out of 6 pieces in one whole. So 6/6 is one whole. Now if we did it again with maybe, I don't know, let's go 4 2/3. Then if you have 4 wholes and you cut them each into thirds, you have 12 thirds. Because 1/3 is 3, or 1 whole is 3/3, and you have 4 of them altogether. So quadruple that, and you'll get 12 thirds plus 2/3 makes 14 thirds. And this 12 plus 2 business came from the fact that 4 wholes is 12 thirds, and you have an additional 2 thirds to tack on. Okay, let's go in reverse. How do we change improper fraction into mixed one? Okay, so let's take a top-heavy improper fraction and turn it into a mix of wholes and parts. So let's suppose for fun we have 22 fifths. Well, I know that I can break that into 20 fifths and 2 fifths to get 22 fifths, and 20 fifths is actually 4 wholes. Okay, and a lot of people take a little bit of a shorter avenue and say that how many times does 5 go into 22? It goes in 4 times with a remainder of 2, which is exactly what I did behind the scenes in my head, because really I was asking myself, how many wholes can I get out of this? Well, 20 fifths, or 5 times 4 makes 20, so 20 divided by 5 will make 4 wholes here. And so I was thinking the same thing, just written differently. Before I make my last remark about fractions and then kind of summarize what this whole topic was about, I'd like to mention that a lot of my students do these fractions, these mixed and improper fractions, using some kind of fraction thing on their TI-83 or TI-84, whereby it immediately writes it as either form for you. I just wanted to show you the why and the how, because you will have to show why and how and explain that. So might as well just, you know, get used to that, the showing of why and how things work. And then my last remark is that people really prefer simplified fractions, and it's just because they're more relatable. For instance, this half versus that 22/44, like I mentioned earlier. So people prefer simplified fractions. Because they're relatable. There are times in your life when you will use fractions for yourself, and there are times in your life when you will have to use fractions for somebody else. And the reality is that most people, they just simply prefer the simplified version. Okay, now I'm going to take it just to summarize what we did. Really, we started from scratch, but we used, remember, all different kinds of wholes are applicable to fractions, and then there's a difference between fractions and ratios too. And every time we do some form of arithmetic, it really should be representable in some realistic form at its core level. Why we create mathematics is as a tool and usually as a communication and a quantifier. We like to make measurements. Every day we decide what every object is worth in terms of monetary value. And that in its own right is a measurement. So our wholes, they just vary for every representation we have in life. And when we're doing things like equivalent fractions, right, we should be able to represent it. And in addition to that, we should be able to do it arithmetically too. Okay? Make sure that if you are making comparisons, you label everything. Units are the same as your whole. The next video on fractions is all about the operations.